Hello, everybody. I'm Silas, and welcome to Psilocybology. Let's expand our mind. This is a series where we talk about the research on psilocybin, the psychedelic prodrug found in magic mushrooms. We'll be breaking down and discussing the scientific literature, one study at a time, from past to present. If you'd like to support the show, please make sure to rate, review, and subscribe to the podcast. Today's episode is on the article titled The Effects of Psilocybin on a Test of After-Image Perception, published in 1965 by a researcher at the University of North Carolina, Chapel Hill. It's actually the same primary author that conducted the research we discussed last week, although the focus of the study is very different. The impetus for this study comes from the well-documented phenomenon that psilocybin produces changes to visual perception. What hasn't been as well documented is what biological processes are influenced by psilocybin that ultimately produce these changes to our visual perception. The author of this study thought that using a test of after-image perception could possibly help elucidate such processes. Let's discuss what after-images are. We've briefly mentioned them on a prior episode of the podcast, but let's take some time and revisit them so we know what exactly this experiment was testing. A simple example of an afterimage is when you look at a light source, not the sun, please, and then look away. You can sometimes see a dim area floating in your vision that is left behind. Afterimages are also related to the experience of tracers. Tracers are when you see trails left behind moving objects, which are relatively often reported by individuals after taking a psychedelic. One common example that I've heard people talk about when reflecting on their experiences with psilocybin is that sometimes when they move their hands rapidly across their field of vision, their hand will look like it leaves a trail behind it. When discussing afterimages in a bit more detail, there are importantly two types of afterimages: positive afterimages and negative afterimages. Positive afterimages are when the afterimages you see are the same color or relative brightness as the original image. Negative afterimages, on the other hand, are when the afterimages experienced appear to be inverted in color or relative brightness. I'm not sure how many others may have come across this example in a textbook at one point, but I remember in some science class I took that they showed us an image of an American flag that had black stars on a yellow background and stripes that were black and green. If you stare at it for 30 seconds or so, and then look at a completely white surface and blink, you'll see a flag that is the normal red, white, and blue. Now, this study specifically examined negative afterimages, rather than positive afterimages. So let's talk a bit more about how negative afterimages occur. To do this, we first have to talk a bit about the structure of our eyes. At the back of our eyes is our retina, which contains two types of light-sensitive receptors called rods and cones. Rods help us see in low light settings because they are more light-sensitive, which allow us to see in the dark and also contribute to our peripheral vision. Cones, on the other hand, are less light-sensitive and are instead primarily responsible for color vision. This is why colors don't look very vivid in low-light settings. One important feature of photoreceptors is that they can lose sensitivity by adapting to overstimulation. In other words, our rods and cones can sort of tire out when being subjected to a particular stimulus for a prolonged period of time. The reason this fatigue produces an afterimage has to do with the fact that humans have multiple types of cones, each that code for complementary colors. When a cone is being stimulated by one of the colors it is receptive to, it also inhibits the perception of the complementary color. As silly as this analogy might be, it might help to imagine a single cone as if it's in a perceptual arm wrestling contest with itself, where each arm represents one of the two complementary colors that a given cone responds to. Also imagine that colored images that you'd be looking at are cheerleaders in this analogy. These cheerleaders are supporting the colored arm that they represent. Let's take the cone that responds to the colors red and cyan as an example, when you go from staring at a red image to a white image. The arm wrestling match starts off with a team of 4 red cheerleaders and no cyan cheerleaders. This amps up the red arm, allowing it to hold down the cyan arm. This is then what allows you to perceive red when looking at a red image. Now, switch out the red image for a white image, which importantly is the combination of all color wavelengths. All of a sudden, 3 of the red cheerleaders have to leave, leaving only 1 left. At the same time, 1 cyan cheerleader arrives. Even though it's ostensibly balanced with 1 cheerleader for each side, the red arm is tired from having held down the cyan arm for so long, and so it doesn't get very excited by the single cheerleader. This fatigue can be more technically called post-excitatory inhibition. The cyan arm, however, just gained new support, so it's able to draw the full amount of energy from the 1 new cheerleader. This allows the cyan arm to temporarily overpower red, and is why a cyan negative afterimage is produced when shifting your focus from a red to a white image. Eventually, they balance back out once red isn't as tired. This is of course an oversimplification, but I think it fulfills the need for this podcast. The reason you don't see negative afterimages all the time is because our eyes are constantly making tiny micromovements that shift light onto different parts of our retinas, making it so no particular receptor is responding to the exact same stimuli for too long. This is why when trying to induce a negative afterimage, you're asked to stare at a specific spot on an image for a prolonged period of time. Hopefully that provided enough of a foundation to get started. I have a feeling if something doesn't quite make sense yet, going through the study might help. So getting into the study, this experiment was conducted on 10 young adults. The author doesn't provide much information about the participants, since that apparently wasn't common to do back in the 60s, but they did mention that, quote, they were known to conduct themselves in accordance with conventional social mores, which struck me as an odd thing to include in a scientific paper. The other thing the author noted, that isn't particularly relevant, but I got a laugh out of it, is that participants, quote, agreed not to be alone in a house or apartment, not to attend social gatherings, and, if unmarried, not to date until the day after leaving the experiment. Wouldn't want psilocybin to cause them to violate any social mores, I suppose. Anyway, the crux of the study is that they wanted to see how the administration of 0.2 milligrams of psilocybin per kilogram of body weight influenced the participants' performance on a test of afterimage perception. The test that they administered involved an episcodoster, which is a device we've seen on a prior episode. But fortunately, this study does a much better job of describing exactly how the device was set up. Essentially, participants looked through an eyepiece that was 2 millimeters in diameter, and through it they saw a colored spot in the center of a white background. The colored spot cycled between representing a red stimulus, a white stimulus, and a black stimulus, repeatedly in that order. The cycling of the 3 stimuli was caused by a rotating disc, which was divided into 3 sections. There was one 30-degree circular sector that displayed the red stimulus, a 180-degree circular sector that displayed the white stimulus, and a 150-degree circular sector that displayed the black stimulus. Since the disc rotated 5 times per second, this meant that for each rotation, the inner circle in the center of the white background was red for 0.017 seconds, white for 0.1 seconds, and then black for 0.083 seconds. Who said geometry wouldn't come in handy one day? The key manipulation used by the experimenters, in addition to psilocybin, was the luminance, or how bright the white stimulus appeared to participants. Interestingly, prior research had shown that there are luminance or brightness values of the white stimulus below which participants reported perceiving the color red when looking through the eyepiece, and above which were participants reported seeing the complement color, cyan, which the authors note was described as blue-green by participants. This means that this technique induces a negative afterimage that suppresses the perception of the stimulus itself. Given this prior research, the author specifically wanted to see how psilocybin influenced the luminance threshold needed to produce the afterimage, as this might tell the author how psilocybin impacts our visual perception. It's important to note that up until this point, when talking about afterimages, we've been discussing what happens when you remove the original image and simply start staring at a white background. The reason this experiment is different is because it involves flickering back and forth very rapidly between the image and the negative after image. When this flicker occurs fast enough, you only selectively perceive the image that is the most vivid. This can be influenced by how bright the white stimulus is presented. So in this experiment, the participants were split into two groups. At 9 a.m., half of the participants received psilocybin, and the other half received a placebo. Participants were not told which they were given. Researchers also then administered the test in order to have a baseline value. Then, at 11 a.m., the participants who had received placebo were given psilocybin, and those given psilocybin were given placebo. The test was also re-administered to all participants. Finally, participants were again given the test at 1 p.m. Now, interestingly, one thing the researchers found is that between 9 a.m. and 11 a.m., the threshold for how bright the white stimulus needed to be in order for participants to see cyan increased for everyone. However, the increase seen in those given psilocybin was much greater than the increase seen after being given placebo. In addition, the threshold decreased between 11 and 1 for those given psilocybin at 9 a.m., indicating a return to baseline, whereas the threshold increased between 11 and 1 for those given psilocybin at 11 a.m. This indicates that psilocybin does appear to increase the luminance threshold, but that it may also increase a bit on its own throughout the day. When we start to interpret what this means, the author notes that the precise mechanism involved had not been proven at the time of publication, but they put forward an interesting hypothesis. They essentially state that the color seen, either red or cyan, comes down to the total net excitation. If there is greater total excitation for the color red than cyan, the participants report seeing red. If there is greater total excitation for the color cyan than red, participants will report seeing cyan. What's important to note is that there are two sources of excitation in this experiment, that from the red stimulus and that from the white stimulus. No excitation comes from the black stimulus, since that's really more of the absence of a stimulus. So the red stimulus, obviously, produces an excitatory response for the color red. The white stimulus, meanwhile, provides an excitatory response for both red and cyan, since white contains all colors of light. That said, the fatigue or post-excitatory inhibition that we discussed earlier causes the level of excitation from the red portion of the white stimulus to be blunted, whereas the level of excitation from the cyan portion of the white stimulus is unimpeded. So here we have two sources of red excitation and one of cyan. The other important part of the experiment lies in the luminance of the stimuli. The red stimulus is kept at a constant brightness of 25 millilamberts, while the luminance of the white stimulus is manipulated and ranges from 4 to 150 millilamberts. As you increase the brightness of the white stimulus, what you're really doing is disproportionately increasing the level of excitation in response to cyan compared to that for red, due to the post-excitatory inhibition that inhibits the level of excitation elicited from the red portion of the white stimulus. There is therefore a threshold where the white stimulus is so bright that the excitation in response to cyan overcomes the combined excitation produced by the red stimulus and the red portion emitted from the white stimulus. Part of this is influenced by the fact that the red stimulus is only shown for 0.017 seconds per rotation, whereas the white stimulus is shown for 0.1 seconds per rotation. The researchers thus believe that the increased threshold seen after being given psilocybin is a result of a decrease in post-excitatory inhibition, because this would require the white stimulus to be much brighter in order to cause participants to see cyan. Personally, I had a lot of difficulty at first wrapping my head around this, but what surprisingly helped was to turn this into a formula. I'll include it in the transcript if anyone is interested in seeing what I wrote out. I think it would be a little bit too hard to verbalize. It's not meant to be offered as a legitimate proof of anything. It just helped me visualize what the author was hypothesizing and may help others understand the concept. The key takeaway is that the authors interpreted this data as indicating that psilocybin reduced the amount of post-excitatory inhibition. Now, one thing that adds a layer of complexity to the interpretation of this study is that while we've spent a lot of time focusing on the rods and cones, it's actually unclear whether the effect of psilocybin is due to its influence on our retina or on our brain. More recent research has cast doubts on whether afterimages are produced solely by properties of the receptors in our retinas, as there is some evidence to suggest our brain also plays a role in our perception of afterimages, although its role isn't yet fully understood. The author notes that, quote, "It is possible that the effects of psilocybin are mediated at other levels of visual integration, besides the retina." This finding, if it truly is a result of a decrease in post-excitatory inhibition, could also help to explain other visual phenomena that occur after being given psilocybin, such as the tracers we discussed earlier in the episode. The author states, quote, "A relative decrease in inhibitory as compared to excitatory reactivity in cone-based processes that mediate perception of color and detail would favor such imagery produced by psilocybin." Now, while the findings we've already discussed have been interesting, there was actually another component of the study. In addition to the afterimage test, the participants were also asked to complete a 32-item checklist every hour from 9 a.m. to 2 p.m. on the day of the experiment. This checklist asked them about a number of visual changes, which were categorized as either major changes or minor changes. Fortunately, the author actually included the full questionnaire in the appendix, so I'll go ahead and put those items in the transcript as well. What the researchers ended up doing was ranking the participants based on how much their luminance threshold increased and how many visual changes they reported 120 minutes after being given psilocybin. These values turned out to be correlated, such that those who reported more visual changes also had a greater increase in the luminance threshold. Finally, before wrapping up today's episode, there was one small detail I wanted to mention. After being given psilocybin or placebo at 9 a.m., the participants were asked at 11 a.m. to tell the researcher which they thought they received. The author noted that one of the participants given psilocybin at 9 a.m. reported that they believed they actually were given placebo. What was interesting is that this participant reported the fewest number of visual changes after being given the drug, and had one of the lowest increases in luminance threshold, comparable to the increase seen in one patient after legitimately being given a placebo. The reason this piqued my interest is because I've always been fascinated by anecdotal reports I've come across where some people don't feel anything during their first time using some drugs. I remember first coming across this with cannabis, where I knew of friends who ate an edible for the first time and felt nothing, while others who ate an edible from the same batch definitely felt the effects. I've also heard of similar situations happening on occasion with first-time users of psilocybin. In these anecdotes, there are often too many confounding factors to understand what happened. One thing that's interesting about this participant is that he was given pharmaceutical-grade psilocybin, so it's not like he got a couple of low-potency mushrooms. I'm really curious how many other people may have come across this first-time tolerance and what might be behind it. It could ultimately be nothing, or rather a bunch of contributing factors, but I think it would be such an interesting line of inquiry. Anyway, that's it for today's episode. As always, I really hope you enjoyed the show. If you have any questions, feedback, or ideas for the podcast, please let me know. You can find out all of the ways to reach me on the website, psilocybology.org, where you can also find the full transcript for each episode if interested. Thank you all for listening, and I'll talk to you next time.